Okay, so we will go to next problem. We will look at problems now related to recycle streams. So far what we have been trying to do is, if you look at some of the problems that we have done so far uh, related to material balances with reactions. So you see that some of these problems, even if they were a fairly long problem, say for example, where were we, even if you look at a problem, yeah, something like this ethylene glycol problem, we had so many unit operations and unit processes that were involved. In terms of reactions were there, in terms of separation processes were there, sulfuric acid kind of problem where there was some recycle, uh, but we would like to see more general way of looking at recycle problems. And even this kind of problem where we looked at ammonia synthesis problem, well, there were multiple units, right from reformer, partial oxidation, shift reaction, CO2 removal, and the ammonia synthesis. We have been doing problems with multiple units. Uh, all of these problems, if you think about, there you could either solve it from the front, that is the left end, that is the raw materials end, and go all the way up to the product end. So you could solve it from left to right, so to say, in terms of from raw materials to products. Or you could take basis as 1 kilogram or 1 mole of ammonia and work your way backwards and solve from right to left, or from product end right up to the raw materials end. Now we are going to look at recycle problems and how some general strategy of how to solve these kinds of reactions and these kinds of problems, and some terminology associated with these problems or with these kinds of recycle streams as well. So here is a problem. We will straight away start with a problem. I will let you do the problem, and then I will explain some of the important terms and some of the important concepts. So we have a stream containing an aqueous solution of glucose. So if you see some of your food products, there are things like high fructose corn syrup, because fructose is supposed to be more sweeter than glucose. And how are glucose and fructose related to each other?
Isomers.
Sir, one is aldol, another is keto.
Right, so they are isomers of each other. So it is possible to convert one from the other. So this is a problem that looks at converting glucose into fructose. So let's say we have an aqueous solution of glucose. Let's say it is a 40% by weight aqueous solution of glucose, meaning if I take 100 kilograms of the mixture, 40 kilograms will be glucose, 60 kilograms will be um, water. So we are going to look at a feed solution, let's say 100 kg per hour. It's a continuous process. So this is going to go into reactor. Isomerization reactor. So this isomerization can be done catalytically, can be done enzymatically using enzymes. So, but we are not worried about how it is being done. We are only going to say that glucose is isomerized. And of course, it does not require water for the isomerization. It is just a um, uh, rearrangement of the glucose molecule into a fructose molecule. So water is like an inert here. It is just a solvent. Now, what comes out of the reactor is, of course, water, unreacted. There is no reaction of water. Some of the glucose gets converted to fructose. So what comes out of the reactor is water, glucose, and fructose. So the conversion is not 100%. So some of the glucose remains unreacted. So this glucose also has to be utilized in the sense that we want to recycle it back. So part of the stream is taken, and that part of that stream is recycled back to the reactor. So this is your recycle stream. I should draw a nice straight line. It's kind of difficult to draw. Yeah. So this is our recycle stream. Of course, we don't recycle everything because then there'll be nothing to sell. So that's not done. So we take out our product and it is partly recycled. So this is a continuous process. We are operating at steady state. That means we don't have to worry about when the plant was started, where this recycle stream came from. Don't worry about that. Maybe when the plant was started, we will recycle everything and slowly we will start taking out product. But soon we will reach a steady state and we are looking only at the steady state solution. So this recycle stream is going to contain water and glucose and fructose, right? And this product stream is also going to contain water and glucose and fructose. So this recycle stream is going to mix with this fresh stream. Fresh stream is of course going to contain water and glucose. So in terms of nomenclature, this is called as fresh feed. All right. Okay. This recycle stream and the fresh feed mix, and that together is called as combined feed. And it is this combined feed that goes to this isomerization reactor. So obviously when I mix a stream of water and glucose and mix a stream of water, glucose and fructose, I will have water present, glucose present and fructose present. I know something about this combined feed in terms of weight percent. I don't want fructose coming into the isomerization reactor so much. So I will want to limit the amount of fructose coming into isomerization reactor. So remember, the isomerization reaction is glucose going to fructose, and it is usually an equilibrium reaction. But let's not worry about that just now. Let's assume that it is an irreversible reaction. But I would like to limit amount of fructose that comes in, because that is unnecessarily wasting my volume in the reactor. So I would like the fructose in the reactor feed to be just 4 weight percent. Okay. I know something about this recycle stream as well. So I will tell you something about the recycle stream. The ratio of the recycle stream to product stream. So flow rate, mass flow rate of recycle stream to mass flow rate of product stream. This ratio is, for this particular case, it is 0.12. Okay. This ratio is called as recycle ratio. Just some nomenclature. Recycle ratio. So the recycle ratio is ratio of the recycle stream going back to the reactor and the product stream going out of the plant. Okay, so that ratio is 0.12 for this particular problem. Right. Now what I want you to do is find out the quantities and compositions of all the streams per 100 kg per hour of the fresh glucose, fresh feed, which is containing 40% by weight aqueous solution of glucose. There is no fructose in the fresh feed. Okay, so I will let you do this problem and then we will talk about more about this problem. So just to help you get started, remember, write different quantities that are present in the form of tables: weight percent, kg per hour, weight percent. That's our general strategy, how we have been solving these kinds of problems: kg per hour, weight percent, kg per hour. Write down what you know. Even in the recycle stream, you can write weight percent and kg per hour. This is your recycle stream, kg per hour. Right, write down all the things that we know. We know that in the fresh feed it is 40% by weight glucose. So this is 60 weight percent, water is 60 weight percent, glucose is 40 weight percent. Total basis we are taking as 100 kg per hour, so this would be 40 kg per hour, 60 kg per hour. Right, so write down all the things that we know and try solving this problem.
So one
Yes,
question.
yes.
Would the fructose isomerize to go to glucose?
Well, glucose is a major component. So it's an equilibrium reaction. Some glucose will go to fructose, some fructose will go to glucose. But overall, it is overall thing that we are worried about. Right now, let's assume that it is an irreversible reaction. So only glucose is going to go to fructose.
Okay, sir.
Okay, so fructose does not react.
Sir,
Yeah.
sir, is there any percentage conversion of glucose to fructose?
No, that is not known.
Okay, sir.
In fact, that's one of the things that we need to find. How much should be the conversion in the reactor? Do you think this problem is more complicated than the previous ones? And if so, why do you think it is more complicated?
Sir, fructose is not converted, right, in isomerization.
What is not converted?
Fructose, fructose is not back to
No, no,
glucose,
no.
right?
We are treating it as a irreversible reaction. Only glucose is going to go to
Okay, sir.
fructose. That's why I have written that arrow G going to F. I did not write the reversible arrow. Do you think it is more complicated than the others? No, nobody is thinking anything. Are people using unknowns X, Y, Z, P, Q, R, A, B, C?
Yes, sir.
How many?
Sir, 3, X, Y, Z only.
So far, three.
Yes, sir.
Okay. Anybody using two unknowns? Nobody is using two unknowns. Anybody using four unknowns?
सर वाटर की जरूरत नहीं थी फिर भी लिया है उसको.
फिर भी लिया है, ठीक है, ले लो. Anybody using one unknown?
Sir,
Yes.
that recycle ratio is for each stream or for total?
Total. You say mass flow rate of recycle stream divided by mass flow rate of product stream.
Okay, sir.
Recycle stream means everything inside. Product stream means everything inside. Isn't it?
Yes, sir.
Yeah. How many are using two unknowns? Anybody is using two unknowns? Just unmute yourself and answer. I'm using two unknowns. No? Nobody's using two unknowns. Everybody's using three unknowns. Anybody using one unknown? Anybody using five unknowns?
Sir, one unknown.
One unknown. Okay. Anybody using zero
Yes, sir.
unknowns?
One.
One. Anybody using zero unknowns? One unknown. Means variables x, y, z. That's a better way to say. How many are using variable? How many are using two variables? X, y. Just unmute and answer. How many using three variables? How many using five variables? Anybody using no variables?
Sir, percentage conversion from glucose to fructose is 93.3%.
Okay, 93.3%. So you are saying percent conversion of glucose to fructose is 93.3%. Okay, that's one answer.
Sir, in the product stream, uh,
Yes.
weight of water is 60 kgs.
Okay. I don't
Weight
know.
of,
I have not solved. You're
yes,
telling
sir.
me or answering me? You're telling me or asking me?
No, I'm telling, sir.
Okay, so this is good. Good in the sense this is good enough answer that if you know this, you will know everything.
Okay, sir.
Now, so everybody just stop for a minute. Don't proceed with calculations. There is an important term with respect to uh, percent conversion. Now that Arya has told percent conversion, I need to discuss one more thing. What is this percent conversion? Um, if you look at this reactor as a control volume, amount of glucose reacted divided by amount of glucose coming in multiplied by 100 is our percent conversion. Do we agree? Do we disagree? Anybody? People should answer. I don't want to be
Agree,
talking
sir.
to myself. Okay,
Yes,
fine.
sir.
Right now, we can we can define this percent conversion in two ways. One is if we take this yellow control volume, then it is the amount of glucose reacted in the reactor, because our control volume is over the reactor, divided by amount of glucose entering the reactor into 100. This is also a kind of conversion across this yellow control volume, which is our reactor. This is called as per pass conversion. Per pass, meaning that every time that much amount of glucose enters, that much amount of conversion will happen. Whereas if you look at it as a whole plant as a control volume, let's say this green control volume, this green control volume, if you take, then we could write for this green control volume, we could write it as amount of glucose reacted in the whole plant, and there's only one place that glucose is reacting in the plant, that is the reactor, divided by this amount of glucose entering the plant, that means the green control volume, into 100. That is also like the conversion across the whole plant, right? So green control volume is the whole plant, yellow control volume is our reactor. So this is called as overall conversion, right? So we could define two conversions. One is a per pass conversion and one is an overall conversion, right? Do we agree with this? Do you agree? Any doubts?
Oh, so in overall conversion,
uh,
would we take the amount of fructose that is there in the product?
Conversion, how are we defining? Amount of glucose reacted divided by amount of glucose entering. Whether that glucose is making fructose or making something else, it is amount reacted.
So like then my answer would change. That's why I'm
No,
asking.
no, I'm only asking you this 93.3%, that is an overall conversion that you're telling me, or per pass conversion that you're telling me?
So like
What is your control volume for defining the conversion, yellow or green? You
it's not
recall?
yellow.
So it is green.
I'm not sure. That's why.
No, no, you can't be
Sir,
not
it's
sure.
yellow. I got the same answer. It's of yellow.
Okay, so
For us.
remember how we are defining. Just let me take you back. We are talking about conversion and selectivity. Do you remember we were talking about that? Conversion means whatever comes in, whatever reacts out of whatever converts. That is our conversion. Whether it goes to fructose or whether it goes to uranium, it is hardly our concern. Well, it is our concern, but it is hardly our concern when I define conversion. Do you agree, Arya?
So like my doubt is that
Huh?
if you take the green control volume
Huh?
and you say that the amount of glucose reacted, would it include
Amount of glucose reacted. Period. Reacted means reacted.
so overall or for the input that I've given?
Green control volume. If it is green control volume, it is overall, no? What is reacted? What comes in minus what goes out. Maybe I will rephrase the word reacted little bit better. Maybe I will say that it is amount of glucose. Now there is no other thing that is happening to glucose. So amount of glucose in minus out. In minus out must be what is reacted, right?
Okay, sir. Yeah. Then okay. Yeah.
Glucose in
Then
minus
I
out.
then I've given the overall conversion, sir.
Praveen, what is your answer? Overall or per pass?
Sir, I first gave the per pass conversion,
No,
but the
no.
overall
This
conversion.
93.3%, you are saying you got the same answer as Arya. So
Yes, sir.
Arya is saying that it is overall conversion.
No, sir, it is a per pass for that reaction only.
Okay. So we have now two answers. Overall conversion. There is one answer, 93.3. Oops, sorry, not 9.33. 93.3. That is one answer. And we also have per pass conversion. Answer and frequency 93.3. Answer is the same. Only thing is one is per pass, one is overall.
Sir, my overall is coming 93.3 bar. The 3 is continuous with infinity.
93.33333. And this also is same. Per pass is same or different?
So it's different. It is 93.30.
30. Oh, only question of 0 and 33333333. Check your calculations, Praveen.
Yes, sir, I will check.
Okay, besides Praveen and Arya and Ria, anybody else doing the problem?
Yes, sir.
Yes, sir.
So tell me, how many variables are you using? 1, 2, 3, 4, 5, 6, 7, 8,
So
9,
one.
10, 11. 1. Okay. So that means only one more person doing the problem.
Sir, I am using three variables. XYZ.
3 variable. Rishikesh, thank you for answering. So now 4 people are doing the problem. 5 people are doing the problem.
Sir, I am using only one
Sir, I'm
variable.
also using three variables.
Nishant, you're using
Three
3
variables.
variables.
Yes, sir.
Very nice. Karthik, how many you said?
Three.
3. Okay.
Even I'm using three variables.
Okay. Ansh, you're using 3. All right. Um,
Sir,
anybody using, yeah,
I am using two variables.
2 variables. Okay. Anybody using no variables, 0 variables, then they are eligible to get a chocolate from me. Anybody using 0 variables? No unknowns, X, Y, Z, nothing. If you're using 0 variables, make a note that you will get a chocolate from me. If and ever you come to ICT, you can meet me and take your chocolate.
Sir, sir, please no if and ever we want to come.
You can come just like that. I mean, you don't have to come to classes. Any other answer for per pass conversion? Any other answer for overall conversion?
So 2 minutes, sir.
Yes, yes. Take your time. Abhay, are you there? Any answer? Are you stuck
No, sir,
anywhere?
still, sir,
Doing
trying.
okay, okay. Are you stuck anywhere? Do you need any hints?
No, sir.
Okay, don't need hints. Fine. Amol, are you there?
Yes,
Are you doing? Are you stuck?
sir, solving.
Solving. Okay. Do you need any hints?
No,
Darshan,
yes, sir.
solving, not solving? Are you stuck?
Solving.
Do you need
No,
hints?
sir. No, sir.
Okay, okay. Prajot, are you there?
Yes, sir.
Do you need any hints?
Sir, I will try myself, sir.
All right, fantastic. I like that spirit. Try, try. Any answer, Ria? You started solving.
Sir, I got stuck, so now I'm restarting. So it's very confusing.
Ah, okay. Why do you think this problem is confusing?
Sir, because of the recycle stream,
Hmm.
I mean, I don't know. From the combined field, like we're getting something back in the combined field, and we have to add it and then reconvert it.
So
There are too many numbers.
yeah. So if you think about this problem versus, let's say, other problems that we have done, like the ammonia problem, which was only one directional. Either you could go from left to right or right to left. Whereas in this problem, you end up going around in circles. So do you think there is a way to convert this kind of problem to a one-way problem like the ammonia problem?
There might be, sir, but I can't realize that now.
Okay. Think further. What can we do to the recycle stream to make it like a one-way problem?
Yes, sir.
Sir, we can take it to another isomerization reactor, recycle stream, and then make it
Uh,
the products.
so you want to add one more reactor here, but
Sir, sir, instead of recycling it, like,
instead of recycling it, okay, 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 and do what?
sir, the isomerization reactor we can add.
But then you
So
are
it will
changing
give
the
the
problem
product.
itself. There is only one reactor. There are no two reactors. You are on the right track, but you tell me properly what is in your mind. Can you elaborate?
Sir,
Yeah, Praveen.
sir, I'm checking. Sir, we have to in overall or the conversion, we have to
Uh,
take the 40 of the fresh feed and
I
the
don't know. What is
end
your
product
control
of the
volume?
glucose
What is your control volume? Green or yellow?
green.
Green. So then tell me, if it is a green control volume, this is how your plant will look like, isn't it?
Yes, sir. So we have to take 40 from the fresh feed and the product finally we got it that is 2.667.
If it is yellow control volume, then it is, that's why the concept of control volume. What is it that we are doing material balance for? Over what control volume? That
Sir,
is,
then my answer is right then 93.3333 bar.
that is overall.
Yes, sir. That's overall.
So Ari also had the same answer.
Yes, sir. Like it was recurring only.
Uh,
93.332
I,
something.
I I know that. I know that. So Ari, what is your per pass conversion?
So it's 92.58 something.
Okay, let's round off to 92.6. So Praveen, check your per pass conversion. There's some problem in your material balance. Okay, shall we solve? Do you need more time?
The 5
Sir, a
minutes
few more
more, please.
minutes.
Okay,
5 minutes, sir.
okay. If anybody is interested in having breakfast, they can continue having breakfast and continue solving problem. Any answer, Ram?
No, sir.
Are you stuck? Do you need hints?
No, sir.
Okay. Are you solving?
Yes, sir.
Okay. So Arya, try doing this problem without any unknowns. Praveen, try doing this problem without any unknowns, without X, Y, Z.
Okay, sir.
So we can.
Yes, we can.
Sir, but in that also we are subconsciously taking variables only.
No, subconsciously means if you say that 2 plus 3 is equal to 5 and you are saying 2 plus x is equal to 5, then the x must be 3. I mean, that's not really, we are not solving any equations per se. I mean, it's I mean, you're not writing equations and solving them. It's um, it's mental.
Sir, I also got 93.333
Per pass or overall?
overall.
And per pass.
Survey time calculator.
So we can do it without variables.
Excellent. I will show both ways, one without variables and one something we will do to the recycle
Excuse me,
stream.
sir.
Yeah,
93.38, sir.
that is per pass or overall?
Per pass, sir.
Per pass is 93.38. Okay, and overall?
So calculating.
Okay. Atharva, you are clear about what is meant by per pass and what is meant by overall, right?
Yes, sir.
Okay, should we solve?
Yes, sir, we can do it without
Yes,
variables.
sir.
Yes, sir.
Okay, so doesn't matter whether you got the answer. If you have not got the answer, let us try to solve. Stop whatever you are calculating, just pay attention to what I am saying. uh, Now if you think about this problem, um, water and glucose are coming in. There is a recycle stream that contains water, glucose and fructose. They mix together. Combined feed goes to the isomerization reactor. Water, glucose and fructose come out. Part of it is recycled and partly it is sent as a product. So if you think about this green control volume, right? So the green control volume is like this. So that's your overall plant. You have a fresh feed coming in, you have a product stream going out. So if you write in terms of kg per hour, water is 60, glucose is 40. So if you think about the total amount of product going out in terms of kgs per hour, in terms of kgs per hour,
Since it is steady
if
state, it should be
yes
100 only.
yes, so if you're talking about the overall plant, there is only one stream coming in, that is the fresh feed, and there's only one stream going out, that is the product. So if the feed coming in, fresh feed coming in, total is 100 kg per hour, then the total product going out must also be 100 kg per hour. Okay? There is no nuclear reaction happening. And if water going out is 60 kg per hour, water is not participating in the reaction, water is not getting generated in the reaction, water is not getting consumed in the reaction, water is behaving like an inert as a solvent, then water going out in the product stream also must be 60 kg per hour. Okay, but we can't say anything about glucose and we can't say anything about fructose, because glucose is getting converted to fructose. Glucose coming out in the product stream must be less than 40 kg per hour. Product coming Fructose coming out in the product stream must be more than 0 kg per hour, more than what is entering, right? So if you think about this green control volume, this total also must be 100 kg per hour, and water must be 60 kg per hour, right? Now if you, what do we know? We know the recycle ratio, right? That means we know that if 100 kg per hour of the product stream is going out and recycle ratio is 0.12, that means the total quantity of the recycle stream must be 12 kgs per hour. Do you agree with that? If the recycle
Yes, sir.
stream is
Yes,
12
sir.
kgs, if the recycle stream is 12 kgs per hour total, and fresh feed is 100 kgs per hour total, the combined feed must be 112 kgs per hour total. Now go the other way around. The stream leaving the reactor, is split into two streams, one product stream and one recycle stream. Recycle stream is 12 kgs per hour, product stream is 100 kgs per hour. So the stream leaving the reactor must be 112 kgs per hour. Okay. Look at the product stream. Water is 60 kgs per hour. Total is 100 kgs per hour. That means weight percent of water is 60 weight percent. Now look at this point where the stream coming out of the reactor is split into two streams. If it is split into two streams, the compositions of those streams must be identical. So water in the stream leaving the reactor must be 60 weight percent. Water content in the recycle stream must also be 60%. Oops, why it is doing like that? Now look at the recycle stream. If water is 60%, total is 12 kgs per hour, then kgs per hour of water must be 60% of 12. That means 12 multiplied by 0.6. That means 7.2 kgs per hour. Okay. Now look at this point. Where the fresh feed meets the recycle stream and they mix and go as a combined feed. Water coming in from the fresh feed is 60 kg per hour. Water coming in from the recycle stream is 7.2 kgs per hour. So the water going in the combined feed must be 67.2 kgs per hour. Okay. Now, if you look at the reactor, water coming in is 67.2 kgs per hour. Water is not reacting. So water going out must be 67.2 kgs per hour. So far, so good. Do we agree? Do we disagree?
Yes, sir.
Agree.
Okay. What else can we say? What else can we say?
Sir, the amount of fructose that is in the combined feed
Right.
is solely the contribution of the amount of fructose over here.
Over here means
So,
which stream? Over which
in
stream?
the recycled stream,
Right.
so 4% of 112 would be equal to the amount of fructose present,
Correct,
that is
correct,
kgs per hour in the recycle stream.
correct, correct. So we are coming to that. We are coming to that now. Now look at this combined feed. It is 112 kg per hour total. 4% of that is fructose. So fructose kg per hour must be 4% of 112. That means 112 multiplied by 0.04. So this fructose in terms of kgs per hour in the combined feed must be 4.48 kgs per hour. Now again, if you look at the point where the fresh feed and the combined feed, fresh feed and the recycle stream are mixing, 4.48 kg per hour is there in the combined feed fructose. There is no fructose coming from fresh feed, so all that fructose must be coming from recycle stream. So in the recycle stream we must be having 4.48 kgs per hour of fructose. Now we are almost there. Look at the combined feed again. Total is 112 kgs per hour. 67.2 kgs is water kg per hour and 4.48 kgs per hour is fructose. So the balance 112 minus 67.2, sorry, 112 minus 67.2 minus 4.48 would be the glucose stream. And if you calculate that, sorry, 67.2 glucose stream is 40.32. Again, look at this point where the fresh feed and the recycled feed mix. Glucose coming in is 40 kg per hour. Glucose going in the combined feed is 40.32 kg per hour. So that means this 0.32 kg per hour of glucose must be coming in from the recycle stream. Okay, we are almost there. Okay, in the recycle stream, water is 7.2 kg per hour out of the total 12 kg per hour. That means it is 60%. Glucose is 0.32 kg per hour out of the 12 kg per hour. So percentage of glucose would be 0.32 divided by 12 into 100, which is 2.67%. Fructose is 4.48 kg per hour out of the total 12 kg per hour. So 4.48 divided by 12 into 100, fructose must be 37.33 weight percent. Okay, now look at this point once again, where the stream coming out of the reactor is split into two parts, one recycle and one product. If it is split into two parts, the composition must be the same. Then weight percent of water is 60%, glucose must be 2.67% by weight, and fructose would be 37.33% by weight. Okay, and obviously now we know the weight percents and we know the total quantity, so we can get kg per hour here. And this stream coming out of the reactor must also have 2.67 weight percent glucose and 37.33 weight percent of fructose. And we know the composition, we know the total quantity, so we can calculate the kgs per hour. And we know the quantities and compositions now of the combined feed as well, because we know the kg per hour, we know the total quantity. So we have used no variable at all for solving. Now look at the overall plant green control volume.
Sir, so the purpose is
One second,
92.69 only.
one second, Praveen, one second. Look at the green control volume, the overall plant. What comes in is fresh feed, 60 kg per hour of water, 40 kg per hour of glucose. What goes out as a product stream is total 100 kg per hour, 60 kg per hour is water, 2.67% of 100. So that means this glucose must be 2.67 kg per hour. 37.33 weight percent of the total 100 kg per hour. That means fructose must be 37.33 kg per hour. So if you look at the percent conversion overall, what enters is 40 kg per hour, what leaves is 2.67 kg per hour. So that means 40 minus 2.67 kg per hour is what is reacted in the plant, divided by what comes in is 40 kg per hour. So the percent conversion is 40 minus 2.67 divided by 40 into 100, that is 93.33%. Okay. If you look at the reactor, if you look at the reactor in terms of kgs per hour coming in terms of kgs per hour going out, the reactor, the yellow control volume, total coming in is 112 kg per hour. Total going out obviously must be 112 kg per hour. Water coming in is 67.2 kg per hour. 67.2 kg per hour. Glucose coming in is 40.32 kg per hour. And fructose coming in is 4.48 kg per hour. Okay. Water going out is 67.2 kg per hour. Glucose going out is 2.67. Oops, sorry. This is the green control volume. Okay. 67.2. Okay. Glucose is 2.67 weight percent of 112 kg per hour. So the kg per hour of glucose going out is 2.67 into 112 divided by 100, which is 2.99 kg per hour. Fructose, it is 37.33 weight percent of 112 kg per hour. That means this must be 41.81 kgs per hour. Right? So to glucose going out, yellow control volume, glucose going out is 2.99 and fructose going out is 41.81. So if you want percent conversion in the reactor, which we call as per pass conversion, what comes in? 40.32 kg per hour comes in, minus what goes out, 2.99 kg per hour goes out. That means the difference 40.32 minus 2.99 is what has reacted, divided by what is fed, 40.32 kg per hour into 100. Right? So this is 40.32 minus 2.99 divided by 40.32 into 100. This is 92.585958%, 92.6% if you like. Okay. Anybody has any doubts, any issues, anything we need to discuss once again? Just unmute yourself and ask. I can't take names of 53 people and ask everybody. Are there any doubts? Are there any issues? Anything we need to discuss? Should we go to the next problem?
Sir, sir, just one doubt, sir.
Yes,
Uh,
yes.
in between, is in between, sir. The water composition. I'm able to understand that at the end, in the final composition, the kg per hour is 60 for water. But
Right.
in between, how is the weight percent 60, sir? I wasn't able to understand that.
No, no, we didn't write from there. We got that 60. We didn't assume it to be 60. We calculated it to be 60, and it is correct because water is not reacting. And glucose and fructose are, there is an isomerization reaction. So molecular weight is not changing, moles are not changing. So the weight percent remains 60, but we didn't assume it to be 60. We calculated it to be 60. So this 60 you got.
So how, sir?
We have to go all the way.
Yes, sir. 60.
We
That.
have to go all the way back because I'm I'm writing as it is. So this is 68%. Do you agree with that? I have to use blue color.
Yes, sir.
Blue color. Okay, so 68%, right? If this is 68%, this also must be 68%, because this
Sir,
it is the same.
how, sir?
It
As
is the
in,
same stream that is split into two parts. If you take air in your room and you put part of the air in a bottle, will the weight percent, mole percent of oxygen and nitrogen in the bottle and the rest of the room change? Are you doing any separation or are you splitting the whole stream?
oh, okay, sir. So, understood, sir. So without any reaction, the composition will remain the same, provided there's no
And
reaction.
provided there is no reaction, provided there is no separation.
Separation. Oh, yes, sir. Yes, sir. Understood. So the
Long,
same stream is being split into two.
long ago, we had a seawater. We had a reverse osmosis, and we made drinking water, and we had a reject. So there we are separating. Sodium chloride and water is getting separated.
Yes,
One
sir.
getting enriched in water, one getting enriched in sodium chloride. So here we can't say the composition remains the same because we are doing the separation,
Yes, sir.
right? Whatever stream comes out
Yes,
of
sir.
the,
Understood,
yeah,
sir.
whatever stream comes out of the reactor, that whole stream is split into two parts. One is taken out as a product and one is recycled back, and the ratio is 0.12 recycled ratio. All right.
Yes, sir.
Okay.
Yes, sir. Thank
Yeah,
you, sir.
no problem. Can we go to the next problem? Next problem is going to be slightly more complicated. Not just slightly more complicated, it's going to be way more complicated. Shall we go to the next problem? Yes, no? Anybody has any doubts?
So we can go to the next problem.
Yes,
Okay.
sir.
Yes, sir.
Okay, so here is the next problem. We are making methanol. Methanol, we are reacting by carbon monoxide and hydrogen in the gas phase to give us methanol in the gas phase. This is a high temperature and high pressure reaction. Let me do you a favor. I will balance the reaction as well. So carbon monoxide plus hydrogen giving you uh, methanol. Now, obviously, this is an equilibrium reaction, right? For the purpose of the problem, for simplicity, we are just assuming that it is uh, just irreversible. Okay, so there is a fresh feed. Fresh feed. This fresh feed is a gaseous stream, high temperature, obviously, because the reaction is at high temperature, contains hydrogen, carbon monoxide, and methane. Methane is coming from steam reforming. That's how we generate the syngas of carbon monoxide and hydrogen. Recall our ammonia problem in terms of volume percent or mole percent. This is a high temperature gas stream, high temperature and pressure. It is a gas phase reaction. So hydrogen is 67.3 weight percent. Carbon monoxide is 32.5 weight percent.
Sir, volume percent, no?
Yeah, volume percent. Volume percent and mole percent are same. And methane is 0.2%. Okay, again, it's a continuous process. We are only looking at the steady state. Okay, so this goes to a reactor. In the reactor, carbon monoxide plus hydrogen react. 2 moles of hydrogen react with 1 mole of carbon monoxide. Giving you methanol. There are 2-3 other reactions happen, but let's just for our simplicity, just for this purpose of this classwork, we are saying that only one reaction happens. It's a high temperature, high pressure reaction. So everything is in the gas phase. Now, this per pass conversion of carbon monoxide is 18%. 18%. Okay, so obviously all the carbon monoxide does not react. So carbon monoxide is there, hydrogen is there, methane is an inert, that is also there, and the methanol that forms by way of the reaction, that is also there in the gas stream leaving the reactor. Okay, so far so good. How do you think we will separate the methanol from the carbon monoxide, hydrogen, and methane?
Cooling down.
Right, so we will cool down. What will happen to the methanol?
Liquefies.
Correct. Methanol liquefies. And this is like our water condensation problem. So this gas stream that goes out, liquefied methanol will be liquefied and the gas stream will go out. What can we say about this gas stream? What would be the methanol content in that gas stream? Recall our humidity and saturation kind of problems that we did, where we condensed out water. What did we say about the air remaining?
100% RH.
Right. So that means, what can we say about this gas stream leaving the condenser? Suppose this condenser is at a temperature of 50 degrees centigrade. What can we say about the gas stream?
100% saturated.
Means what? What can we say about partial pressure of methanol in this gas stream?
It is equal to the
Vapor
vapor
pressure of
pressure.
methanol.
Equal to the vapor pressure,
of methanol at what temperature?
50 degrees Celsius.
50 degrees centigrade. Okay. So just to make your life simple, this is the reality. But just to make your life simple for the purpose of this problem, we are going to say all the methanol condenses in the condenser, and the gas stream going out has only carbon monoxide, hydrogen, and methane. There is no methanol there. But that is not correct. Okay. But just to make the life simple just now. Do you agree with that?
Yes, sir.
Yes, sir.
Do you agree that I am doing you a favor?
Yes, sir.
Okay.
So could you please repeat the last part?
See, in the humidity and saturation problem, when we had water condensing out, we had, let me go to that problem, wherever that problem was. I can't, see, where we had liquid water condensing out. What did we say about the air going out of that condenser? We said that it was 100% saturated. It had 100% RH. Do you agree?
Yes, sir.
And therefore, partial pressure of water vapor in this air must be equal to vapor pressure of water at this temperature, because we are cooling to 20 degrees centigrade. And that's how we calculated the humidity, isn't it?
Yes, sir.
So same way here, methanol is condensing. So this gas stream going out, suppose it is condensing, we are cooling it to 50 degrees centigrade. This gas stream will have partial pressure of methanol equal to vapor pressure of methanol at 50 degrees centigrade. So this stream will also contain methanol in the gas phase. But just to make your life simple just now, not every time, definitely not in exams, just to make your life simple just now, we are going to say that all the methanol condenses and no methanol goes in the gas stream. Just to make your life simple. It is not correct, but just to make your life simple. Is that
Understood,
okay?
sir.
Okay.
Yes, sir.
So this is incorrect. Don't do it ever. It is only for the purpose of this problem. Don't do it in exams. Don't do it the rest of your lives. Okay. What do you think we are going to go to do to this gas stream? What should we do to this gas
Recycle.
stream? Recycle.
Recycle.
All right. And mix with the fresh feed. So this is your fresh feed. This is your combined feed. We are going to mix them. Now, do you see a problem? Do you see a problem? If you take this whole thing as a control volume, methane is coming in. Is there a place where methane is going out? Is there a place where methane is going out? Is methane,
Sir, it will accumulate.
it will accumulate, right? So right now, suppose to start the plant, we have 0.2% methane. After some time, it will become 0.5%, 0.7%. If I look at the methane content in this combined feed, it will keep on increasing, right? Because methane is coming in all the time. Methane is not reacting. Methane is not going out. So this combined feed will have methane will keep on accumulating. Finally, you will have only 100% methane getting recycled. Nothing will be, very little carbon monoxide will be there. Very little hydrogen will be there. So I need a stream to take out that methane, right? So that stream we call as purge stream. Purge is something that is sent out of the product, purged. out of the system. It is taken out, and then the rest is recycled back. Okay. So this purge stream also will have carbon monoxide, it will have hydrogen, it will have methane. And recycle stream also obviously will have carbon monoxide, it will have hydrogen, it will have methane. The combined feed also will have carbon monoxide, it will have hydrogen, it will have methane. Okay, is the problem statement clear to everybody? And coming out of the reactor, obviously I will have unreacted carbon monoxide, unreacted hydrogen, methane inert, and the methanol that is produced by the reaction. Right, is the problem statement clear to everybody? I know something more about this process. This purge stream, so if I have more of purge stream, I will have less of the recycle stream. Do you agree with that?
Yes, sir.
If I purge
Yes,
everything,
sir.
there will be no recycle stream. If I purge very little, there will be a lot of recycle stream, and methane will keep on building up. Methane concentration, steady state methane concentration will be more than 0.2%, depending on how much I am purging and how much I am recycling. I know something about the purge stream. I know that the purge stream, methane content of the purge stream is 3.2%. Right? So we control the purge stream so that the methane content in the purge stream is 3.2%. Obviously, it is much more enriched than 0.2% because we are recycling a lot of it. We are purging small amounts. All right. Is that okay? Is the problem statement okay so far? Here is what you need to find. Find out quantities and compositions of all streams per 100 moles of the fresh feed. Okay.
Sir.
Yeah.
So can you repeat why we have added the purge stream?
If I don't add the purge stream, just if I take the overall control volume, methane is not reacting. Methane will keep on accumulating because methane is always coming in from the fresh feed. Then my reactor will see a lot of methane, very little carbon monoxide, very little hydrogen. That's not good because I want to make methanol from carbon monoxide and hydrogen. So we add a purge stream so to control the extent of methane that builds up in this recycle, combined feed and reactor, this loop. This
Yes,
loop.
sir.
So depending on how much purge I take out, to that extent methane will get built up in the loop. So
Yes,
I
sir.
am taking out purge stream so that the purge stream has 3.2 volume percent of methane. Okay, so
Yes, sir.
so that it does not build up in the loop. Okay, it's a gas. Everything is in the gas stream. So mole percent and volume percent, they are same. So find out quantities and compositions of all streams, and basis you can take as 100 gram moles of fresh feed. If you like 100 gram moles per second, per minute, per hour, whatever is your favorite time unit, because it's a steady state process. Okay, that's one thing. Second thing I
So,
want you to find out is overall conversion. 1 second, yeah. Overall conversion, just 1 second, Arya. Overall conversion of carbon monoxide. Yeah, Arya, go ahead.
Sir, could you please show the definitions for the different types of conversion again?
Yes, yes, yes. Across the reactor, it is called as per pass conversion. Across the whole plant, it is called as overall conversion.
Okay, sir.
So here it is per pass conversion is 18%. Means across this yellow control volume, conversion of carbon monoxide is 18%. I want you to find out the percent conversion across the whole plant, meaning this green control volume. Per pass means it is across the reactor, 18%. If you are stuck anywhere, just ask. I might give some hints. Write the mole percent, write the total moles. Anybody has gone crazy so far? Anybody has done something? I don't want you to actually do this problem till I explain something more. Okay. So if you got stuck, that's fine. It's okay.
Sir, one question.
Yeah.
So the volume percent of methane, that is 3.2%, it would be
Uh,
same for the main gas and a recycle gas, right?
main gas. Which is the main gas? There's no such
The
thing as main
combine of
gas.
the recycle and purge.
There
Purge.
is gas leaving the condenser.
Yes, sir, the gas leaving the condenser.
Okay.
It would be
Yes.
same, right? Volume percent.
Yes. Yes. Because the same stream that is split. Now, these recycle problems, we are going to do them this way. Okay. So just stop whatever you are doing. Let me explain a little bit, and then you can continue. So recall our problems where we did ammonia kinds of problems, where we could either go from left to right, or we could go from right to left, and we can get nicely some answer. Here the problem is complicated because there is a recycle stream that is mixing with the fresh feed, combined feed. It is going back and again generating that recycle stream, and everything is at steady state. So the way we are going to do these kinds of problems is we are going to break this recycle stream. Right? We are going to break this recycle stream. We are going to treat it like a different stream going out and a different stream coming in. Right? So we are going to break that recycle loop, and we are going to say there is a stream that comes in which has carbon monoxide, hydrogen, and methane. And there is a different stream that is going out. This also is going to contain carbon monoxide, hydrogen, and methane. Doing that, what we have done is we have converted the problem with recycle stream into a problem which was like our ammonia problem. We could do it from left to right or right to left. So now this recycle problem, we have broken that recycle stream. Now we can do it from left to right or right to left, whichever one we want. Now there is no longer that recycle stream. We have broken that and made it into two streams. One stream mixing with the fresh feed, and one stream which is going out of the plant. Okay. Only condition that we will have to keep in mind at the end, that the quantities and compositions of this stream coming in is the same as the quantities and compositions of the stream going out of this plant. So the plant now is going to be like this green control volume. There is a stream coming in, there is a stream going out. It is as if we are having two different streams. Okay, but then at the end we will put constraint that the composition and quantities of the stream coming into this green control volume and the quantity and composition of the stream going out of this control volume, they are the same, because it is in reality, it is that this same stream that we have broken into two parts. Okay, so that consideration we will keep in mind. Do you agree with that? This could be one way of solving. I'm just saying it is one way of solving. I'm not saying it is the only way of solving. Okay. Now, if this is the case, since I don't know anything about this stream that is coming into this control volume, which is that broken recycle stream now, I don't know anything about this stream. I am free to make assumptions that this has X moles of carbon monoxide, it has Y moles of hydrogen, and it has Z moles of methane. Okay. Now, if I make that assumption, my basis is 100 moles of the mixture, fresh feed, right? So immediately I can write something about the combined feed. I can say that carbon monoxide would be 67.3 moles plus X moles. Hydrogen, oh, sorry. I should, sorry. I should say that carbon monoxide is 32.5 plus X, right? I better switch this around. I better say this is carbon monoxide and hydrogen 32.5, 67.3. Hydrogen, I can immediately say is 67.3 plus Y. Methane, I can immediately say it is 0.2 plus Z. Do you agree with that? I have introduced three
Yes.
unknowns. I have broken the recycle stream and I've introduced three unknowns X, Y, and Z. Now I have got everything in the combined feed stream, but only problem is it is in terms of X, Y, and Z. Now I can go from left to right. Now I can find this. I can go forward. I know that all the methanol is condensed. I can find this. I can find something about this. Now I will say that this stream going out, let's give some stream numbers. Let's call this as stream 1. Let's call this as stream 2. Let's call this as stream 3. Let's call this as stream 4. Let's call this as stream number 5. Let's call this as stream number 6. Let's call this purge as stream number 7. Let's call this stream as stream number 8. So I have broken the recycle stream and I have generated two streams, stream 2 and stream 8. I have assumed XYZ in stream 2 because I don't know anything about it. Now that I have assumed XYZ, it allowed me to write the moles in stream 3. Now I can go forward and write something for stream 4. I can write for stream 5. I can write for stream 6. In terms of X, Y, and Z, I can write for stream 7. I can write for stream 8 in terms of X, Y, and Z. Now at the end, to find X, Y, and Z, all I have to say is that stream 2 and stream 8 are one and the same. They are identical because they have come about as two different streams because I have broken this recycle stream into two streams, stream 2 and stream 8. So in effect, they are the same, and therefore, to find X, Y, and Z, I will put constraint that compositions and moles in stream 2 and stream 8 composition and moles are one and the same. Okay, that is one way of solving. Okay, so solve using this mode or this manner or this method. At least you will get an answer. Otherwise, you would have ended up going around in circles continuously. That's how we are going to solve our recycle problems. So anytime there is a problem with recycle, the safest way to solve is to break that stream into two different streams and solve it from left to right or right to left. Assume X, Y, and Z as unknowns coming into this green control volume. Is that okay?
So we can also integrate that stream out also, right?
There's no unique way of solving. There are different ways of solving. I mean, you are free to choose your own method, but this concept of breaking the recycle stream into two streams, it will always give you a solution. You will not end up going around in circles.
Okay, sir.
We are breaking the recycle stream. We are tearing that recycle stream and make it into two streams. So let me just write that per pass conversion was 18%.
Also, for the
Yeah.
humidity problems,
Hmm.
the issue that was in the test was that we couldn't find it accurate to two decimal places using the graph. So
Yeah, but
how should
so use the equations.
it was taking a lot of time in that. Actually, that's
One and
where
a half 1.5 hours were there for
the five
solving.
problems were there.
But it was only two problems. Part there was a ventilator problem, and there was this another problem. Right? Which what was that other problem? Ventilator and the tire problem.
The tire one.
Yeah. So tire you didn't have to find anything. It just was tire was a
The tire one was easy. Like,
childish.
yeah.
Everything was just given. It was just made to look like a really big complicated stuff. You just had to do sulfur balance and you would have got everything.
Yeah, that was easy. Like the tire problem didn't give that much of problem. Like
Correct. Yeah.
it was mainly with the where we had to use the equation because that was time consuming. So, uh, is it that we need to practice more problems to acquire the speed, or
Yeah, it will happen automatically. Anyway, it is 1.5 hours should have been more than enough. Uh, it's okay. So midsem also is not going to be straightforward, but it is not going to be having time pressure.
Sir, for mixing the portion itself, what will you doing on Thursday, right?
Anybody's doing, anybody stuck, anybody started? Any answers? It's too early for an answer, but you can still give. Actually, this problem will tell you very nicely. If you calculate this overall conversion of carbon monoxide, you will see that this overall conversion of carbon monoxide is very, very
Sir, can I only
high.
tell XYZ?
You already have XYZ?
Yes, sir.
Okay, so tell me
Sir, X is coming 5.61,
what
Y is
moles or percent?
moles
5.61.
61.
Okay,
H2 of moles is coming 8.92,
8.92. Okay,
and the moles of methane are coming 0.48. 48.
0.48. Okay, now with these, if you do the problem, is your stream 2 and stream 8 identical? Have you used the condition that stream 2 and stream 8 are identical? Praveen.
Yes, sir.
So that means this stream 8 also would have 5.61, 8.92, and 0.48, isn't it?
Yes, sir.
Now, by doing all that, do you have mole percent of methane as 3.2?
Yes, sir. Sir, actually,
No,
I've
no,
done it like
I don't want to know how you've done it. Is it 3.2, 0.48 divided by 0.48 divided by 0.48 plus 8.92 plus 5.61 into 100? That's 3.2. Very nice. Okay. Now, in the green control volume, is your total material balance satisfied? Kgs coming in, kgs coming in, kgs going out, kgs going out, kgs going out in stream 1, kgs coming in, stream 2, kgs coming in, stream 5, kgs going out, stream 7, kgs going out, stream 8, kgs going out. Is your carbon balance happening across the green control volume? Is your hydrogen balance happening? Is your oxygen balance happening? Elemental balances, are they satisfied?
sir, I have to do the all work then.
Check. Then only you will know whether your answer is right or wrong. And you don't have to ask me whether answer is right or wrong. If all these balances are satisfied, then your answer is correct. You don't have to know. You don't have to ask whether it is right or wrong. Isn't it? Okay, shall we stop for the day? Will you be able to calculate by Thursday?
Yes, sir.
Yes, sir.
Okay, so that's your homework. All right, so homework. Okay, so we will stop here for the day. I will stop recording.